for part A, they want a free body diagram. So let this be the sphere that's on the ramp, right? I know that since it's rolling down the ramp and it's gonna, roll forwards, it's gonna need a force that motivates that clockwise rotation, right? So it's gonna need a force that generates that torque. So I know that a static friction that goes up the ramp is gonna be what generates this clockwise rotation. And I know it's going up the ramp because clockwise rotation, and I know it's static friction because static friction is what motivates a rolling object. There's going to be a single point on the ground, and this static friction is what's going to, force it to go around in this rolling motion because it's working against it, and it's not going to let it slide. And I know there's going to be an Fg coming from the center of mass. Really? And that's just going directly down. That's going to be the weight of the object. And I know from the center of mass, there's also a reaction force from the ground. It's going to be an Fn. And this Fn is going to be slightly smaller than this Fg because it's going to be a reaction force that is a component of Fg, the Fgy. So there's the free body diagram. For part B, I have to prove the moment of inertia of this. So let's do that. I know disk is going to be using the area density equation where lowercase sigma is equal to mass over area, right? And this is also equal to, I differentiated the top and bottom, dm over dA, right? So then I know that this sigma is going to be equal to dm and then dA on this side. Okay, so I'm going to have that general expression. I know that the area for a disk is going to be pi r squared, and derivative of that area is going to be 2 pi r, like so. I know that for the inertia equation, I'm going to start with the integral of r squared dm. And let's establish my bounds right now. Since I'm going to be integrating a disk, right? This is going to be the center point, and I'm going to go all the way extended out to the radius, right? So I'm going to integrate from 0 to the radius, and I'm going to sweep around this entire disk. So it's going to be 0 to the radius, right? And I can't integrate by mass because mass isn't a changing value. So I'm going to plug in what I established dm to be, which is sigma dA, which I'll just rewrite. So equal to integral from 0 to r squared of sigma dA, like so. And now I need to I can take out sigma because I know that's going to be constant, which is just mass over area. So I will like so. It leaves me with this from 0 to r squared of dA. But what is dA? That's going to be 2 pi r. And my bad, I forgot a dr here because I know that the r is going to be, a rotating value that's going to gauge my changing motion. So I'm going to have this dr right here. Right, the r is going to come on to this, so it's going to make it r cubed. Integral from 0 to r. This, I'm going to move my constant to the front, which is going to be this 2 pi right here, this 2 pi, and then this sigma. That's going to be 0 to r cubed with respect to r, as so. Then I'm going to integrate r cubed using the integral rule. I'm going to add 1 to the top and divide it by whatever the top becomes. So that's going to equal 2 pi of sigma times r to the power 4 over 4 from 0 to r. Fundamental theorem of calculus right there. Right? The 0 is going to come, the r is going to come in first actually. This will be r to the power 4 still. And I'm going to subtract this by 0 coming in, but when 0 comes in, this term is just going to become 0. So really all I need to do to look at this term is going to make it equal to 2 pi times this mass over area, which I can now put in, where the area is pi r squared, which that was sigma, and it's going to be r to the power 4 over 4. So that comes into, right? So what's going to happen is the pi's cancel out, the m stays here, this turns into a 2 because r squared is taken from this r to the power 4, and this 4 turns into 1/2. So I know that I is going to equal to 1/2 m r squared, like so. Using the center of the disk as the pivot, I'm going to need to derive an expression for the translational acceleration, right? Well, if I use the center of the disk, I can't use FG because I know that FG is not going to have a perpendicular distance. So I'll have to use the FS force, which is going up the ramp. Pretend that's just going up the ramp, right? So I'm going to have to use that FS force, right? But what is that FS force? It's going to be the force of static friction, right? And I know US times Fn is going to equal to Fs, right? So I need to establish what Fn is. Well, I know there's going to be an Fg like this, right? And this Fg is going to be equal to, mass of the thing times g. And I need to get this Fn, which is going to look like that, as the free body diagram dictated earlier in part A. So to get this Fn, I'm going to need to get this Fgy right here. And I know that this angle here is going to be the angle of the ramp, right? So I know that Fg's adjacent component is going to be equal to Fgy, which is going to be equal to Fn. So to get this Fgy component, I'm going to have to do mg times cosine of theta. Like so. This is going to equal to Fgy. And then I'm going to need to do Fn, which is equal to Fgy, so mg cosine theta right here times mu s to get Fs. So Fs is equal to mg cos theta times us. Like so. So now that I have that established, I want the translational acceleration, so I'm going to start off by using what I know about torque to get this translational acceleration. I know that Fr is equal to I alpha. And this is the force creating the torque times the perpendicular distance is equal to the inertia times the angular acceleration. I can expand this right here, this I, to whatever the inertia of the disk is, which I derived earlier, 1/2 mr squared, right? And then I know alpha, I can just change that into translational acceleration over r, because I know a is equal to alpha times r, right? I know this one r cancels out, one r cancels out. I still have Fr here, but what is the F that's creating that torque? Fs. And I know that this r cancels out, this r cancels out, so I have Fs is equal to 1/2 a, the translational acceleration, not angular. And I know that Fs is equal to what I wrote up here, mg cos theta mu s is equal to 1/2 ma. I cancel out the m's from both sides and I multiply by 2, so I have 2g cos theta mu s is equal to my translational acceleration for the center as my reference point. For part D, I'm going to want to do a translational acceleration, except the point where it touches the ramp is now my pivot point. That means I can't use the force of static friction because that's no longer the force generating the torque because there's no perpendicular distance. Now the force generating the torque is going to be my Fgx component, and that's going to motivate the rolling downhill. Well, first to find Fgx, let's draw Fg and come to understand its components. There's going to be an Fgy, as I established earlier, like so. That's equal to the Fn, and now there's going to be an Fgx that points downwards, and this Fgx acts on the center of mass, and I'm just drawing it here to help you visualize it, but that's going to be the force that generates that torque now, and it's going to be the one that has the perpendicular distance. So this is the force I'm going to be using. And I know that this is the angle, so I know that Fgx is opposite to the Fg component. So I know that previously established Fg is equal to mg, right? So if I want Fgx, the opposite component is just going to be mg sine theta. So that's Fgx. Now, like I established before, let's do the Fr equals I alpha, right? 1/2 mr squared right here. Alpha. No, not 1/2 mr squared. 1/2 mr squared would be the inertia of a disk, right? But since I'm shifting the pivot down here, I'm going to have to use the parallel axis theorem, right? And this distance I shifted down is just r. So I know it's going to be plus md squared, but this d is r, so plus mr squared, like so. So that's the parallel axis theorem to account for the inertia now that the pivot has shifted here, because here is no longer the center of mass of the object. Before I was at the center of mass, so I could just do 1/2 mr squared, but now that I have shifted it down to the pivot, I have to use the parallel axis theorem. Like so. Alpha is still here, right? And Fr is like so. But this time it's going to be the Fgx. I'll rewrite that later. So I have like FR is equal to this times alpha. Alpha changes into A over R. Translational, as I established, translational is equal to alpha times R. So I divide R both sides. A over R is equal to alpha. So that's what that's going to transform into. That means I can factor out an R out of all of this. This will cancel out with that. And then this R over here will cancel out with both the R squared, the R's in there after. So both those R's cancel out. I'll just write 1/2 M plus M because all the R's have canceled out. This R squared I factored out. 1 cancels here and then 1 cancels there. So now I'm going to have equal 3 over 2M times A. And this F is going to be the FGX mg sine theta. Like that. And then the m's cancel out. So I'm going to have the A is going to be equal to 2 over 3g sine theta. Like so. So that's going to be the UA. Now they want the free body diagram. I know the block is going to have a weight. So this FG is going to be pointing downwards. And in reaction force to that, there's going to be an Fn, which is pointing perpendicular to the incline. And this Fn is going to be a little bit less because it's a component of Fg. I know there's going to be a tension force pulling the object downwards because now there's a rod attached. And I know there's going to be Fk opposing the line of motion and Fk because it's in kinetic motion. And since it's a block, the friction force against it will be force of kinetic friction. Now for the disc, it's also going to have a Fg pointing downwards. Right? And in reaction, it's also going to have a Fn. A little bit less than Fg because it is a component of Fg that's equal to Fn. And it's also, this time it's going to have a tension force pulling it back a bit from the rod. And this is more directly going to be opposing the line of motion. So I'll draw it bigger than Fs, the force of static friction. It's because the object's rolling, so it's not Fk. And this Fs is going to be pointing upslope, and it's also going to be a little less upslope to continue motivating that clockwise motion, but the tension is going to be bigger because it's more directly opposing this motion, slowing it and maybe even bringing it to a stop depending on the scenario, but in this case it's going to be slowing it. But this T is going to be larger than the Fs. Now to prove this equation, I'm going to start off with the net force, and that's going to be equal to the sum of the forces going down the ramp minus the forces going up the ramp, which is going against that motion. Right? So I know that the block, it's, well, first of all, this F net, right? F equals ma, so then it's going to be 2m times a. This is the linear a, and that's going to equal the forces going down. I know the block is going to have an mg sine theta, which is the FGX force going down, plus the circle is also going to have an mg sine theta. And since I'm looking at this in terms of a system, tension is just an intermediate force, so I don't even need to worry about that. And I know that the forces going against this, there's going to be mg cos theta, which is the Fn of the block times mu k. And then there's going to be the force of static friction that's also going against the motion. This is the force of kinetic friction. To find the force of static friction, I have to use torque, where it's going to be Fr is equal to I alpha, right? And since I'm using for this one, Fs as the force that generates the torque, my pivot point is the center, right? So I'm going to have the normal inertia. I don't have to use parallel axis theorem. So Fsr is equal to 1/2 mr squared times alpha, but alpha is also a over r. This r cancels out and this r cancels out. So I have Fs is equal to 1/2 ma. And I do this because I can't just do Fn times mu s because it's a circle and the circle's motion is different. I have to use this torque expression to find what Fs is. So I know Fs is equal to 1/2 ma, so I can just do 1/2 ma like this. I know that m's are all going to cancel out. So I'm going to have 2a is equal to g sine theta, like that, plus g sine theta minus cosine theta mu k minus 1/2 a, right? So I'm going to add 1/2 a to the other side. This simplifies to 5 over 2a by adding 1/2 a to both sides. And these two g sine thetas are going to become equals 2g sine theta, right? And it's going to minus, there's still a g here, my bad, minus g cos theta mu k. Like that. Now at this point, I'm going to multiply a 2 to the other side. So this 2 goes away, and this is going to be 4g sine theta minus 2g cosine theta mu k. And it's all going to be divided by 5 now, because I divide 5 by both sides. Like so, right? And now the last step, I just need to factor out a g on the top like the original one did. So it's going to be 4 sine theta minus 2 cos theta uk. And the g's factored out. It's all going to be over 5. And that's the same as this expression up here. 4 sine theta minus 2 mu k cos theta. Well, there's 2 cos theta mu k times g is over 5 is equal to a. So this is the expression that works. Alright, in part F we proved this expression right here, that a is equal to this, right? And in part F we also established that FSR is equal to 1/2 mr little r squared alpha, right? And this is I alpha, and I can do 1/2 mr squared because I'm referencing the center of mass, so I don't need to do any parallel axis theorems to account for shifts. So I know this is just a over r. One r cancels here, another r cancels here. I know that fs is equal to 1/2 ma, right? And if I just plug a in, fs is equal to 1/2 m, right, on top. Then a, which is just g, 4 sine theta minus 2 mu k cos theta, like so, all over 5. This becomes just a 10, and there you have it. My bad, I wasn't finished yet. The final expression, they want the 5 at the bottom, right? So to do that, you just factor 2 out of this. So you get a 2 up here. And this cancels with that, simplifies with that to make it a 5 here. And I factored a 2 out of this, so this becomes 2 instead of 4. And this just becomes minus mu k cos theta. So fs is equal to mg 2 sine theta minus mu k cos theta over 5. Part H, it wants to know what happens to tension if the mass increases, right? So to look at tension, I'll just be looking at the block system, because if I can look at one of the systems, tension is that intermediate force, right? I mean, one of the parts of the system, right? And tension is that intermediate force between. I can evaluate what happens to it. So if I look at the block, I'm going to have the net force of the block, 3ma, is going to equal to 3mg sine theta. And then minus the plus tension pulling it forwards, minus the resistant force, which is going to be 3mg cos theta times mu k, right? And then I'm going to isolate for tension, because that's what I'm looking for is happening to it, right? So I'm going to have T is equal to 3ma, add this to the other side, plus 3mg cos theta mu k, and then minus 3mg sine theta. Theta. Okay, so before I had T equals ma plus mg cos theta mu k minus mg sine theta, right? But now I have 3's in front of all of them because I've increased the mass, right? So this increases by 3 multiplier, this increases by a 3 multiplier, and this decreases by a 3 multiplier, right? If this increases by a 3 multiplier and this increases by a 3 multiplier, 2 terms increasing by a multiplier of 3, right? Then this last term here, also increasing by a multiplier of 3, the mg sine that helps it go down, that reduces from tension, I believe that it's not going to increase more than these two increase. Because first of all, you have 2 forces, resisting forces, that motivate this tension to be greater in comparison to this one force that's helping tension, making it lesser, because of the gravity, right? So this 3, I'm saying that it doesn't grow as much as these other 2. Sure, there could be other things, like let's say mu k was extremely small and the incline was like extremely large, right? But in a realistic scenario where the incline was like this, right, and it had a reasonable mu k, the reasonable justification would be to increase, because if you think about it, you're going to have a block system, right, where the mass has increased, and to move it at that same acceleration as before, because we derived the acceleration expression, and the acceleration expression was independent of mass. To keep it at that same acceleration, you would obviously need more tension to help motivate against that friction, against that restraint bounded by keeping that same acceleration. And that 3mg sine helping you, I believe it wouldn't grow as much, so I claim that tension will increase.